Hi guys, this lesson is going to involve kind of a lot of stuff, so lock in. Uh, what we're going to be looking at this lesson are called inverse functions. Now, we're not going to jump straight into them. We're going to sort of build up to them step by step, so that we've got a sense of what we're dealing with when we deal with inverse functions. Now, the first thing we're going to be doing is we're going to have two functions. We're going to have a and we're going to have b. Each one is really just a set of points. There's no real pattern to them. We're just going to plot them out and then see how they compare with each other, A and B, so that we can see the pattern, so kind of compare them with each other. So the very first thing I'm going to do is a little dull, a little slow. I'm just going to plot my points out. So the first one is -6, -4. I'm just going to plot that onto my graph down at -6 and -4. And then I've got -4, -2, which will go here, -1, 0, which will go there, 0, 3, which will go here, 4, 4, which would go here, and 5, 6, which is going to go up here. So this is my first set of points. There's no real pattern to them. It's not meant to be like a sort of graph or anything. It's just a bunch of random points. This is the first thing that I want. Now, what I'm going to do next is I'm going to try and be fancy. This has kind of come back to bite me a few times, so hopefully it won't this time. I'm going to try and switch colors. What I'm going to do is I'm going to now plot my points for B. So I should have -4, -6. So down at -4 and -6, I've got mine still doing the painful stuff. -4, -6 is just going to be down at here. And then I've got -2, -4, which is going to be down here. 0 and -1, which would just be down here. 3, 0, which would be out here. 4, 4, so same point as the one up there, and then 6, 5 is going to sit out here. Okay, so far so good with the pen. Now, what I can see is that if I draw on a line, which is going to be my y equals x line, a dotted line that goes down the middle, then I should be able to see that these two are basically mirror images of each other. So the black ones being above the white line, the red ones being below or on the line. These two are basically reflections of each other in that line, and that's what it's going to mean for two functions to be inverses of each other. So this is basically what we're going to visualize. We're going to get one function, and then we've got to find like its mirror image version, which is going to be on the other side of the y equals x line. We're going to have a bit of a process for doing that. But before we get into how that process is going to work, we're just going to have to write a bit about this. Now I've got a fair bit to write. I'm just going to talk through it, so hopefully this is going to be paced okay. So what I'm going to say is that A and B are inverses of each other. Um, I can say that A and B basically have their x and y coordinates swapped. I should have been able to pick that up on that. If the first one was -6, -4, which was for A, B was -4, -6. The same coordinates, but the x and y's get swapped, and that's the same for every point. Like I had 5, 6 turning into 6, 5. I had, for example, 0, 3 turning into 3, 0. 4, 4 and 4, 4 obviously stay the same, but their x and y coordinates are switching with each other. That's what we expect inverses to do. So the x and y coordinates of A and B are swapped. Now, given that they're inverses, we can also say that, well, we've mentioned this already, they're mirror image versions of each other. So we can say they're mirror image versions of each other. The more technical way we describe it is we'd say that one is the reflection of the other in the line y equals x. So I'm going to write both those out, and you guys probably just want to go ahead and copy those down. Yep. So the other bits and pieces that we'll need to know about functions are, first of all, if I was to call one of these functions, say f, for example, then the other one would be f with the -1 up the top, what we call its inverse function. So I'll write a bit about that, and then I'll talk about what it means. Just want to fix it up so it's extra clear. Sorry, -1 goes up the top. -1 is the inverse function. So if we have function f, f with a -1 up the top, we call this inverse function. Now, that's going to be slightly different to it's like, it looks like the power of 1, but it means something different. It's not so much a power as it's just like a form of notation. So f with a -1 doesn't mean like f to the power of -1. That's some entirely other thing. The inverse function is just the inverse function, and this is how we'd write it out. Now, the final bit we need is that something about a function and its inverse that we can say is that if we look at, say, the domain of the black dots for set A up the top, the black dots run from -6 up to 5 in terms of their x values, whereas the red dots, their y values run from -6 up to 5 in terms of their y values. So what we can say is that the domain of A is going to be the range of B, and the range of A is going to be the domain of B. We've talked about range, we've talked about domain. I'm hoping you guys are comfortable with what those are. With inverse functions, the domain and range of our starting function will be the range and domain of my inverse function. They just flip from each other. Domain of one becomes the range of the other. The domain of range of one becomes the domain of other. So I can say that the domain and range of A and B gets switched. Okay, and if anyone's still writing any of that down, get your teacher to pause the video so that we can you can finish it up before we do the next bit. But this is basically everything you need to know. Well, essentially everything you need to know about inverse functions. That it's about a function and its mirror image version. It gets reflected in the line y equals x. We use certain notation to represent it, and we need to know that the domain and range of the two are basically like switched for each other. Now we're going to go through a couple of examples where we get a function and we've got to find its inverse function. So for the first one that we've got the line 2x plus 4, and we've got its domain as being from x equals -3 up to x equals 1. And what we want to do is find the inverse function and state the domain and range of f minus 1 being our inverse function. So the very first thing I want to do to get a sense of what I'm dealing with is I'm going to plot out my starting function 2x plus 4. What I'm going to do is I'm going to say that it's going to run from -3 to +1. I'm going to find the two endpoints of my graph and then connect them up so I've got it plotted out. So what I'm going to do is say that my graph is going to start at -3. So I'm going to find what the function is at -3. At -3, it's going to be 2 times x. X is -3. Plus 4. 2 times -3 is -6, plus 4, which is going to get me out -2. So when x is -3, y, or my function's value, is going to be -2. So it's going to start at -3, -2. I'm going to just draw a dot here to show where my starting function is going to start. Now, it's going to run up to 1, so I'm going to say that f1 is where it ends. So I'm going to have 2 times 1, then plus 4. 2 times 1 is 2. Plus 4 is going to get me 6. So it's going to go up to when x equals 1, y is going to be 6. So this is where my point's going to sit. And I should just draw a couple of dots along the way so that I've got a bit of a guide for when I connect them up. So this is my starting function. This is f of x equals 2x plus 4. This is what it's going to look like. I'm expecting my inverse function to be like the mirror image version of this function. And so that's what I expect to see when I plot it out. Now, in order to figure out the rule for f inverse, what I'm going to do is I'm going to take this function here. And basically what I'm going to do is where there's the f of x, and the x, I'm going to switch those around. So if my function is y equals 2x plus 4, I'm going to switch the x and the y's. I'm going to switch every x and every y. If there's more than one x, I switch every x with every y. Basically, where there's an x, I put a y. Where there's a y, I put an x. So what I'm going to get is that rather than having y equals 2x plus 4, I'm going to switch the x and y values. I'll just switch x and y to find the inverse. And so what I'm going to get is going to be x equals 2y plus 4. This would be my inverse function. When we write it out, it's normally best to get y on its own. So I want to take this equation and I want to rearrange it. So what I can do is to rearrange this to get y on its own, I can take away 4 to get rid of the plus 4, so it equals 2y, and then I can divide by 2, which tells me I'm going to get y equals x minus 4 over 2, being my inverse function. I might want to write that out just to be clear. I can say f inverse x equals x minus 4 over 2. So my initial function is 2x plus 4. My pen got a little haywire. My inverse function is going to be the x minus 4 over 2. Now, I want to I found my inverse function in terms of its rule. I also need the domain and the range of my inverse function. One thing I might want to do is, in order to get my inverse function's domain and range, I might want to draw it. I could try putting some x and y x numbers into here in order to get some y coordinates and plot those coordinates. What I'm going to do instead is I'm going to cheat. So if I look at the line that I've got to start with, my starting function, it's got coordinates of -3, -2. And it's got coordinates of 1 and 6. What I should know is that to get my inverse function, it's going to have those coordinates, but with those values switched around. So rather than having -3, -2, it's going to have -2, -3 as its start. So I can put that there. And rather than ending at 1, 6, it's going to end at 6, 1. So I can put that in as my endpoint. So I've got my graph drawn out with its inverse function. As I expect, it should be the mirror image version of it in the line y equals x. If it doesn't look like it is, that's normally a sign that I've done something wrong, because that's the way it should be. Now, I can use what I've got here to, I'll just label this as 6, 1, in order to figure out the domain and the range of my inverse function. So I can say that the domain of my inverse function, the x values that it can have, I can see that it starts over at x equals -2, and it goes up to x equals 6. That's where my inverse function is going to end. For my range, the range is just the y values that it can have. So the range of f of inverse, it's going to start down at -3, and it's going to go up to y equals 1. So I've got my domain, I've got my range. I could have tried doing something fancy where if I have a look, my range for my function is the domain of my starting function. So I can say that if I want to save a bit of time, do it a different way, I could have just got my range from looking at the domain of my starting function and said that they're meant to be the same. I could have looked at the range of my starting function from -2 to 6 and seen that that's got to be the domain of my inverse. Whatever floats your boat, either way will get you the right answer. So that's what we're dealing with. We've got a starting function, and we want to figure out what the inverse function is in terms of its rule, maybe in terms of what it looks like, and in terms of what its domain and range are going to be. Now, the next one's going to be a pretty similar kind of deal. We've got a different rule, square root of x plus 4, square root of x plus 4 plus 1. And it's going to run from -4 to infinity as its domain. we want to do the stuff that we just did. We want to get the inverse function. We want to find its domain, and we want to find its range. First thing we want to do, though, is probably figure out what our graph looks like, our starting graph. It's a square root graph. Remember that when we've got a square root graph, we talk about the endpoint of the graph, which is where the graph is going to start. The endpoint is going to be -4 plus 1. I'm just reading off in the way that we kind of read these things off. Starts at -4 and goes, the coordinates are just going to be -4 and 1. So starting over at -4 and 1, that's where our graph is going to begin. Now, what I might want to do, and this will be helpful to me down the track, is I'll also find its y-intercept, because that's just something useful for me to have to graph it. So when x equals 0, or I could say equivalently, since we've got our new notation, I can say h of 0, which is just going to be x equals 0, is going to be equal to 0 plus 4 plus 1. So square root of 0 plus 4, square root of 4, that's just going to be 2. 2 plus 1 gets me out 3. So my line is going to be passing through 3. See if I can get a nice square root looking graph. That's pretty fancy. And just label my coordinates, because that will help me out later on. So there's my square root graph. There's my starting function. Now I should be primed in order to get the inverse plotted out. I could even plot my inverse now if I want to. I could put the reversed coordinates on and then just connect them up. If you want to do that to start with, there's no reason you can't, but I'm just going to move on to getting the actual inverse function. So to get the inverse function, I do like before. Where there's an x, I put a y. Where there's this function, or where there'd be a y, I'm going to put an x. So it's going to turn my equation into y equals the square root of y plus 4 plus 1. I've replaced the x with a y. I've replaced the y with an x. I want to do like I did before. I want to rearrange my equation to get y on its own, so I can see what the inverse function is going to be. So what I'm going to do is I'm going to get rid of the plus 1 by taking away 1. I'm going to get rid of the square root sign by squaring both sides. So it's going to turn into x minus 1 squared equals y plus 4. And then I'm going to get rid of the plus 4 by taking away 4. So that's going to turn it into y equals x minus 1 squared minus 4. Again, using my notation for inverse functions, I might write this out as h inverse of x equals x minus 1 squared minus 4. So I'm expecting it to be a parabola, inverse of a square root graph being a parabola sort of makes sense, since square roots and squares are opposites, inverses you'd say. So that's the kind of graph I'm expecting. I've got my inverse function now. What I might want to do is draw some points out. So what I can do is I can take the left point, which was -4 minus 1. I can turn that into -1 minus 4. Which, if I read off my equation for my inverse, that's going to be, well, something's going on. Oh, hold on. Actually, don't hold on, keep going. I'm going to turn this into -1 minus 4, which is going to sit down here. And then I'm going to turn 0, 3 into 3, 0, which is going to sit out here. Now, hold on. What the hell? I had to pause the video while I realized my mistake. This should have been a positive 1, so that should be at 1 minus 4 rather than 4 minus 1. That explains why I was going wrong. Okay, now I've got my parabola. I can just sketch it out, try and get it like that. And I've got my my inverse function plotted out, which is what I'm hoping to do. Do my quick check. Is it a reflection of it in the y equals x line? Looks to be. They do look like they're symmetrical around that point, which always an encouraging sign. Now, the final thing I want is the domain and the range of my inverse function. So what I'm going to do is just look at my graph, and I can say that the domain is going to be the x values that it can take on. I can see that the x values for my inverse domain are going to start at 1. That's where my graph begins. And they're going to extend upwards all the way to infinity. My graph's going to go continually to the right, even if my the actual graph doesn't actually show that. Similar thing for the range. I can look at my range and see that for H inverse, it's going to start down at -4. It's going to extend upwards to infinity. I better just do a quick check to make sure I haven't. Yep, that's all good. That's basically my domain and my range. I can do a quick check to make sure that I'm right. I've got my range down here. It should be the same as the domain that I started out with. The fact that it is a good sign to me. Good Lord. Okay. So second example is just the same kind of deal. It's just we can go about doing this in a few different ways. We can take our equation, switch the x's and y's, rearrange to get our inverse function. And then if we've got our graph plotted out, it becomes pretty easy to see the domain and see the range as well. Questions are going to look a lot like that. Now, the last example we're going to be going through is this one's going to involve a lot of space because there's kind of a bit to it. But what we want to do is we've got a function which is going to be x plus 3 squared minus 4. What we want to do is first of all explain why the inverse function g inverse does not exist. We've got a domain of R and that's going to be relevant to that on that front. Then we want to state a restriction on the domain of G so that an inverse function exists. So this one's got kind of a lot going onto it. But the very first thing we can do is we've got a parabola. It's got a turning point of -3, -4. So I can just draw that out to get a bit of a sense of what I'm dealing with. What I'm going to do when I draw my parabola is I'm going to want to have at least 2 points. So if I've got my turning point at -3, -4, and I should just label that, what I might also do is try and find the x-intercepts for this. They will help me out down the track. So to find my x-intercepts, I'm just going to say that x-intercepts are going to be when y equals 0, or to use the new function notation, it's going to be when g of x equals 0. So 0 equals x plus 3 squared minus 4. To solve this equation, we can just plus 4 to both sides. So 4 equals x plus 3 squared. We can take the square root of both sides. So the plus or minus square root of 4, which will be plus or minus 2, is going to be equal to x plus 3. And then if we've got x plus 3 equal to plus or minus 2, this is going to have two solutions because we expect two intercepts for this particular graph. So if x plus 3 equals positive 2, then x is going to be equal to -1. If x plus 3 equals -2, then x would be equal to -5. So -1, -5 are going to be our two x-intercepts. So I can just draw my graph. It's going to come down here. It's going to go up, and I think it goes through 5 as well. Now, the reason I drew this graph out is because I want to now explain why the inverse function g inverse does not exist. And the point is going to be that this is a function. It passes the vertical line test, which is the test for whether something is a function or not, but it doesn't pass the horizontal line test. A horizontal line through it is going to cross through 2 points, which means it's going to count as what we call a many-to-one function, not a one-to-one function. And the key idea is going to be that for an inverse function to exist, our starting function, whatever g or x or h happens to be, has to be a one-to-one function. So that's what we're going to write. For an inverse function to exist, our starting function has to be one-to-one. Because this function is not one-to-one, an inverse function does not exist. I'm going to write that. You guys just got to copy it down. Okay. So we've answered the first bit. It says explain why the inverse function does not exist. It's not a one-to-one function that we've got. It doesn't have an inverse function. It'd be nice if that was in the notes because it's a key point, but you should have it now. So now we've got to do the second bit. State a restriction on the domain of G so that an inverse function exists. Now we've seen this before. We've seen that if a function isn't one-to-one, we can split it in half by restricting the domain in order to make it into a one-to-one function. So what I'm going to do is I'm going to split my graph in half. I'm going to delete its left side, and I'm going to restrict its domain so that it starts at -3 and then continues on to infinity. So we're going to have to go outside the box. So if the domain of G is going to start at, I believe it was -3, right? Yep. If it starts at -3 and it runs to infinity, we'd have G of x would be 1-to-1, and then inverse function would exist. Okay. Now, the question doesn't ask us to figure out what the inverse function is, but I'm just feeling a little lively, so I figure we'll do that as well, just to make sure we've got a bit of practice at how that is going to operate. So what I want to do is I want to get the inverse function of this, plot it out, write what its domain and range would actually be, do all the stuff we were doing for the example before. So what I'm going to do is I'm going to do what I've done a few times by this point. I'm going to switch the x and y values. I'm starting to run a little low in room. So I'm going to get x equals, and it was x plus 3 squared minus 4. I'm just going to double check before I proceed that I'm not going to use the wrong one. There we go. I want to rearrange this to get y on its own, so I can plus 4 to both sides. So I get y plus 3 squared. I can take this square root. Because I've only got half of my parabola, I'm only going to consider the positive square root of my graph. Now, to know whether it's right to take the positive or the negative square root, basically when I plot these out, I should be able to see which of the two square roots it should be. In this case, I can just say it's going to be the positive one. I've checked, so that's why I'm confident that I know. But if you're not, you can always just try plotting them and see which one it would be, a positive or negative square root. Now I've got that equal to y plus 3. Last thing I need to do is get y equals square root of x plus 4. Then minus 3 being my square root graph. And again, I'm just going to write this out as g inverse of x equal to the square root of x plus 4 minus 3. So that's going to be my graph. It's going to have an endpoint at -4, -3. So it's going to have an endpoint down here. And what I can do is something similar to what I did before. I can say that my initial graph was at -3, -4, and it had an intercept at -1, 0. So this graph is going to go through 0, -1 because it's like the inverse. It's going to pass up through here. There we go. This one went up through 5, so this one should go down here at 5. And we just do a quick check, draw a line down. Is it the mirror image? Looks pretty good to me. That's a good sign that I've got my inverse graph. Last step, domain, is that if I look at my square root graph, it starts at -4 and it runs up to infinity. So -4 to infinity would be my domain. The range is it starts down at -3 and runs up to infinity. So that would be my range. So I'm going to say that the domain of G inverse is going to be from, and I've already forgotten, -4 up to infinity. And the range is going to be from -3 up to infinity. That's a lot of stuff. This video is like half an hour long now, so I'm not going to keep dragging on. Questions are from 5G. A lot of the questions don't tell you to draw the graph, but often it's useful too when you think that's going to assist you in like figuring out the domain and the range. But the key bit is going to be like the switch X and Y bit. That's going to help you find those inverse functions. That's basically it. You guys just have the remaining part of this lesson to try getting those questions done.